Hello, and welcome to my talk about constructing generic algorithms. If indeed you are out there, which I assume you are. We're going to talk a bit about why we should construct algorithms, and then we're going to do a case study of a non-trivial algorithm which isn't in the standard, and we're going to sort of iterate on it and see how to take it from a piece of code that just exists, today in a function somewhere that isn't at all generic, and make it into a properly generic algorithm that's worthy of something like the STL. Then we're going to talk a bit about principles for algorithm design based off of that. And along the way, we'll point out a few places in the standard where things aren't maybe quite how they should be right now. But of course, before we start, I have to say, if you want to understand the STL, you need to understand the algorithms because they are the soul of the STL. The STL is really not about containers. It's about algorithms for me. And one word about ranges. Everyone says STL algorithms are not composable. You might have heard this even at this conference. I don't say this. Ranges don't give us composability. They give us laziness. They don't actually change the fundamentals of what it means to write an algorithm and what we have to think about. But more on this later. Yes. In fact, the STL algorithms are a study in composability. They're all designed to support stable sort, which in the mid-90s, an in-situ stable sort was pretty amazing thing because it had been a research problem in Knuth. And so, as has been said before, the algorithms fit together like puzzle pieces. So why would we write more? Well, the standard set is great, and we should definitely know them, but it was never designed to be complete. And there are many, many algorithms out there, many choices. I've made some choices for this talk. It's at least partly subjective, but I hope that by the time we're finished with this talk, you'll have a good grounding in the kinds of things that you need to think about in formulating an algorithm. And in a way, the fact that it's subjective is the point. There isn't just one way to solve a problem. We get to formulate an algorithm under our own choices and still stay true to the spirit of the STL algorithms. So let's go ahead. As luck would have it, last year's CppCon provided a good problem. So on the board, someone wrote this. Given an array of unique 64-bit integers in a random order, create a practical algorithm which returns an integer which is not in the array in linear time. Okay, so here's the problem. And this problem could crop up in several circumstances like giving out tickets or scheduling or maybe some other cases. There are many ways to solve this problem. It's not a very difficult problem to solve, but it's not trivial, and it's about the right size for a talk. So let's think about it. The first thing we do when we think about a problem is, what are the constraints? Let's understand them. So it says 64-bit integers. And even if we don't start out that way, we'd like this to be generic. So we can imagine not just 64-bit integers, but maybe chars, right? So it's quite possible that the space could be, at least the overlap part of the space could be full. So we can't just sort of do largest plus one or something like that. We're told we have unique elements, and we're told they're in a random order, which says to me that we're free to change that order, because if we get things in a random order, then we are free to sort of permute them. And it says a practical algorithm, which says two major things for practical are suggested to me. One, it should be no more than linear time, and two, we'd really like to do it in place. These are always the constraints that we sort of like to stay with in algorithm land. Now, there are various suggested solutions to this problem at CppCon last year. One of them was, in fact, a very popular one was radix sort, which is okay, but it didn't seem very general to me. Some people suggested bit twiddling, which seemed even less general and sort of limiting to integral types from the get-go. And like I say, I'd like to end up generic, even if we don't start out totally generic. So the first observation to make here is that if these things were sorted, we'd already be done with a standard algorithm. We'd just run adjacent find or equivalently mismatch. This works fine for a sorted range. We'd be done. this is just the first attempt. This solution works. It is linear, but of course sorting isn't linear. So that's a fairly large constraint to have to throw out. It's usually a good idea, though, to start out by solving a simpler problem, seeing how you can either take away constraints or sometimes add constraints. Sometimes it's easier to solve a more specific problem. Sometimes it's easier to solve a more general problem. In either way, if you solve a simpler problem, it often gets you some part of the way to solving the bigger problem. So a quick aside about adjacent find. Somebody tweeted this, made of mistake, tweeted this a few months ago, I think in May. It happened on Twitter. And of course, the solution in C++ is precisely adjacent find two repeated elements. And just a note about this, a lot of people tweeted solutions to this, and a lot of my Twitter stream is made up of somewhat functional programmers. So people tweeted answers in functional languages. And I have to say that what C++ lacks in beauty, it makes up for in robustness, because many of the other solutions did not support, for example, empty collections. And that's something that standard algorithms give us out of the box. So I'm happy about that. Thinking about adjacent find and mismatch, it's a very common pattern, zipping a range with itself, often shifted in some way. In the case of adjacent find, shifted by 1. Mismatch is equivalent, comparing 2 ranges. In that case, it would be the range and its tail. When we zip a range with itself, though, we do have to be a little careful about iterator category. And that's the fundamental difference between adjacent find and mismatch. Mismatch works on input iterators, and adjacent find requires the forward iterator, because you're going to be looking at things and then returning things in the past. So they mustn't be invalid. And in C++20, we have more things. We have string and string view getting starts with and ends with. And algorithmically, they're exactly the same as mismatch. They're just presented as member functions. So this is an important pattern in algorithms. This is an important pattern, shifted not just by 1, but shifted by n. And we don't get this in C++20 yet. In range v3, there is views sliding, which does something like this. But of course, we can always zip things with the binary version of transform. It's like zip with a binary function. But in terms of standardization, this is still a pattern of algorithm that we're sort of working on in C++. Anyway, back to the problem. So we need a new approach. If we were, like I said, if we can throw away the sorted thing, we're done. But we can't do that. So how do we get a new approach? In answer to Tim, I didn't author any question on the board. Oh, yes. I didn't author the question on the CppCon 2019 board. There was someone else. It just happened to be serendipitous. But that's the problem we're attacking. And we need a new approach. So how do we get one? Well, we're not in grade school anymore. We're allowed to build on the work of our friends, our colleagues, our predecessors. There are thousands of algorithms out there. The main thing you need to know is how to look for them. And this is really what it means being good at algorithms. It doesn't mean coming up with optimal solutions out of thin air. It means knowing the landscape of human knowledge. It means recognizing problems. This is what algorithm intuition is, recognizing problems and knowing what to look for because you know that a solution exists. So with that in mind, we're going to stand on the shoulders of giants and we're going to try the following approach. Now, I'll go through this carefully so that everyone follows. So the approach is basically going to be divide and conquer. We've got this unsorted array, let's say array, of integral types, let's say. And for each element in that array, there's going to be a value there, and it's going to have a position, right? And what we can do is pick the middle of that array. And we can assume that there's only one gap that we're looking for, the lowest. We're looking for the lowest gap, the minimum gap, the smallest number gap. So if we pick the halfway point, P, which we can easily do given the begin and end, and we look at and we look at what's in that now. So this slide is assuming they're still sorted, but we'll get to that in a sec. If we look at the halfway point P and what's in that gap, we know that if it's greater than P, there must be a gap in the bottom half. And so we can recurse on the bottom half. We know that if it's equal to P, there's no gap in the bottom half, so we must recurse on the top half. And we know that when we get down to a sequence of size 1, the answer is going to be the value in our sequence, the next value from the one that's in our sequence. All right. At this point, I'll pause just to see if anyone has questions about the algorithm itself. So again, we're going to take the middle element. We're going to see the value at that position, and according to whether it's greater than the element or no, we're going to recurse either on the bottom half or the top half. I think a sufficient delay has now gone by that everyone, I can assume, is understanding the algorithm. Okay, so here's the first cut, and this is very like this is just where we're starting. So we're just dealing with pointers to unsigned. There's a first and a last, and we're calling out the base, and this is recursive, so we're calling out the base case. If we're down to one element, we're going to return what's there plus 1. Again, we're assuming they're integers at the moment. And then our recursive step is going to say, okay, give me the middle position, M, and then see if what's at that position is equal to what should be at that position, right? And if it is, then we know that the bottom half is full. So we recurse on the top half, doing first plus M for the new first. And if it's not full, we'll recurse on the bottom half, doing setting the last to first plus M. Cool. Now, this doesn't assume the sequence is sorted yet. So what are we going to do about that? What we're going to do is partition the sequence such that it's not sorted, but such that everything less than M is on the left and everything greater than M or equal to M is on the right. We know that partition is linear in time, and it will return the partition point. So at this point, this is what we're going to do to tackle that sortedness constraint. And if we partition, so let me go to the next slide, and I'll show you the code. It's basically the same algorithm, except before we recurse, we partition. And so we get the partition point and say, is it halfway? And if it is, we're going to recurse, we're going to recurse either on the bottom or on the top, according to whether it's halfway. So just a quick note about convincing people that this is still a linear algorithm, right? We're going to partition, and that is linear, order n. We're going to then recurse on half, right? So we're going to get, and we know that we're never recursing on more than half, because we'll always recurse on at most half if it's full minus 1 or the smaller side, right? So we're going to get order n plus n over 2 plus n over 4. So the infinite sum of that is 2n, which is still linear. This is a linear time algorithm. So this is a fair algorithm. We've got linear time. We're doing it in place. There's no extra memory here. I think we can fairly call it practical. So having got a decent algorithm, this is where we start to beef it up. We start to make it more robust. We start to make it more generic. But we've fundamentally got a good start. So the first thing we want to do is test things, right? We've got an algorithm that works. We've got to write some test cases. So good algorithms support zero-length sequences. They support even length and odd length sequences. This is kind of our bread and butter cases. Maybe there's no gap in the sequence, in which case we should return like the maximum plus 1 probably. Maybe there's a sequence that starts non-zero, in which case we want to return probably 0 for the first missing element. We'll come to some choices about that. Maybe there's a gap more than 1, in which case we want to return the minimum missing element. So all of these test cases we can write. And at this point, once we've got it basically working, we should write them. And in particular, testing things like off by one errors with even and odd and empty ranges. They're the good things to start with. So having written those test cases, an important thing to do next is to remove the recursion, because algorithms are usually simpler to think of in recursive formulation. But what we want to end up with is probably a non-recursive algorithm. This original function is recursive, as you can see. Happily, it's tail recursive, which means that the last thing it does is make a call to itself. And after that, it doesn't need to take that value and add it to something or anything. So it's passing along the value down the call stack, so that by the time we're done recursing, we've got the value at the bottom of the call stack, as it were. So we're tail recursive. That would normally be the first change if you have a non-tail recursive algorithm, to make it into a tail recursive algorithm by passing along some accumulated value, such that when you get down to the bottom of the recursion, you've immediately got the value and you don't have to come back up the stack and do more things to it. So that's the first step. Happily, here it's the case anyway. The next thing we do is take the base case usually and make it into a while loop and return after it. And it's usually going to be while last not equal to first. You know, that's a very common pattern because we're going to step first in whatever way until the algorithm's done and there's an empty range left, basically. And then we return the value. And then once we're there, we change our return statements. So before we had the recursive call still in here. Once we've done that, we can change those return find missing elements to simply updating the variables in place. So rather than returning the recursive call, we're going to update first and value in the top half case, and update the end, the last, for the bottom half case. And so in those three steps, we've done that replacement. We've turned a recursive function into an iterative function. So first of all, we didn't need to do this for our thing, but this is usually the first step. You add an accumulator variable to the signature, return it in the base case, and that turns you into tail recursive. Secondly, convert the base case condition into a loop that's typically while first not equal to last loop, and then you return the accumulator value after the loop. And replace recursive calls with variable updates. So instead of rebinding them on a recursive call, you assign them. Okay, couple of questions showing up. Yeah, people asked about the sortedness. They're happy now, I think, that we're not requiring sortedness since we introduced the partition. Question, what is the order of magnitude of n in the problem? We're not yet concerned with that. That's not really a concern here. I think we can say, let's say human scale. We're not dealing with billions of n, and we might not be dealing with 1 or 2 n. You know, so this algorithm, I'm not going to get to the sort of adaptive algorithm stuff where you deal differently with very small numbers or very large numbers. This is going to be more of a talk about how to genericize the algorithm for human scale n. But there certainly are steps you could do that go beyond this talk with adaptive algorithms. Okay, so here we are. This is where we are right now. We've got our while loop in there, we've got our partition in the middle, and we've got our iterative recursion. But perhaps this is the moment you've been waiting for, because it's still not very generic. What's the obvious way to make it generic? Add in templates. So exactly the same algorithm. All I've done is turn those unsigned pointers into iterators. We know it's going to take some sort of iterator pair, first and last, and the result is going to be something of the value type that those iterators point to, typically. So the next question to ask here is, what sort of iterator do we need? What's the category of iterator that we're using? So, quick refresher on iterator categories, which are now concepts in C++ 20. so mostly when we write algorithms, we're using either input or forward iterators, or output iterators are sort of special beast. Input just means you can run over a sequence once. Forward means you can run over a sequence and sort of look in the past, but you can only increment. Bidirectional means you can increment or decrement the iterator, and random access means you can jump around, obviously. And in 20, we got also contiguous iterator. I don't think this is used in any algorithms yet, but it is part of concepts for ranges. So there's a question: if it's human scale, the fastest algorithm is generate a random 64-bit number and do a linear search for it until no collision. Potentially, but a number isn't necessarily generic. What kind of number? Like that? So yes, maybe, but we're going to get to uses for this algorithm which go beyond integers. So these are the iterator concepts. So you look at your algorithm, and how do you decide what kind of iterator concept you need? Well, the first thing you say is, am I using any standard algorithms that require a certain iterator? And if so, then I'm going to also require that iterator. Now, in our case, we're using partition. So partition requires a forward iterator, I believe. So we're going to require a forward iterator. And this also informs your complexity guarantees, because if you're using a standard algorithm, it might have different complexities depending on which iterator category you provide. For instance, with partition, if you give it a forward iterator, it's going to do at most n swaps. If you provide it a bidirectional iterator, it can do its job with n/2 swaps, which is good. So the stronger the iterator you can provide, the better performance you get. But if you can support lower, weaker iterator categories, then at least you get functionality. Now, aside from that, we have to answer the questions: do I look at an element after moving past it? If that's the case, I will need at least a forward iterator, because an input iterator can't do that. Slightly more tricky to spot sometimes is, do I return an element after moving past it? So it's usually fairly easy to see if you're looking at an element after moving past it. It's not so obvious sometimes if you return that element after moving past it. That also would require a forward iterator, because there's no point returning something which the caller's not going to be able to use. Of course, if you need to decrement the iterator, you need a bidirectional iterator. But there's an interesting case here where you might just be looking at, like, the last. You can sort of cache the point where you're looking. Maybe if you're looking just one behind, there could be things you can do there. And if you actually need to increment decrement by more than one to jump around, you might need random access. But again, you can do this in linear time with a bidi or a forward iterator, perhaps. It's just a question of, what you want to support versus the performance that you want. Okay, so what sort of iterator do we? Here's our function again. What sort of iterator do we need? Well, we know that partition requires a forward iterator, and so we will need at least a forward iterator. And so here's what our function signature looks like in 20, and prior to 20, we don't get to use the concepts yet, but it's very similar. In either case, we're using a forward iterator. So we can't do general iterator arithmetic on forward iterators. And in our function right now, on that line, on the fourth line down, we're taking away first from last. And a few lines later, we're adding half to first. So we're going to need to fix up these places, because those operations are not supported by a forward iterator. However, the standard library gives us these handy functions that we can use to manipulate iterators. And these are also implemented to work as efficiently as possible on each iterator category that they can take. And so by using them, we're going to get the right efficiency, the best efficiency for any particular algorithm for any particular iterator that's passed into our algorithm. So even though our algorithm takes a forward iterator, we've got to remember that a random access iterator is a forward iterator. These things are like a hierarchy. So if you have a random access iterator and you pass it and you use stood next on it, you're going to get a jump to the right place rather than a linear add increment. So in this way, we can do pointer arithmetic without losing support for forward iterators. And so we'll relax that line there. We'll go from the actual arithmetic to just saying, let's find the distance. And we'll relax that line there, saying instead of adding, we'll do stood next. And now, so what we've gained here is that we support forward iterators without losing the complexity, without losing the runtime efficiency for stronger iterators. So if we can support a weaker iterator, it makes our algorithm more useful. So what was previously only usable with, random access iterator containers is now useful with containers that provide bidirectional iterators and or forward iterators. Now there's a choice to make here. We might if we decide that we don't want to provide the algorithm for weaker containers because it means a significant performance change that could be a pitfall, that's our choice. But the important thing is that it's a human decision now. It's a business decision. It's not a technical limitation, right? So we might still decide not to support the thing for forward iterators because someone at the call site isn't going to know and they're going to fall off a performance cliff or something like that. That is now not a technical decision, but a business decision, which is what you want. Okay. Do please ask questions as we go. I'll try to answer them as we go. And Tim, the volunteer, will hand them to me. Thank you. Okay, so there are a few places in the standard that the iterator categories don't quite match up to what we know is possible. Partition is an example of this. When Alex Stepanov and Meng Li wrote the STL back in the early to mid 90s, in the SGI implementation, partition takes a forward iterator. When it was standardized in 1998, it was standardized with a bidirectional iterator, and we did fix this in C++11, and it now takes a forward iterator. Stable partition still requires a bidirectional iterator, even though we know how to do it with a forward iterator. The standard hasn't yet had that proposed. So there we go. There's a bit of a mismatch there. In-place merge is another standard algorithm that is currently specified to take a bidirectional iterator, and it's perfectly doable with a forward iterator. And this is one of those algorithms that has a better time complexity if allocation is allowed. It's efficient. It's most efficient if it can allocate a size of at least the smaller of the two halves that you're merging together. So this idea of using the right iterator category, and in particular using stood next or stood distance, is an important step, and it's a specific form of strength reduction. So strength reduction is using a weaker operation to achieve the same effect as a more complicated or stronger, in some sense, stronger operation. It's something your compiler does all the time when it optimizes. It's things like replace a multiply with equivalent shifts, or replace a division by a constant with a multiplication by a huge number, and that strange operation that you'll know if you've ever looked at disassembly for GCC that does that, for example. So this is something the compiler does all the time, but as humans, as algorists, it behooves us to do this to our algorithms, not even so much to achieve optimization, but to see the structure and the limitations of our algorithms. So here are the operations. Here are some operations that we need to consider carefully when we make an algorithm. Decrement, we saw, maybe we can buffer the previous iterator instead of decrementing. Addition as a general thing separately from incrementing, they're different operations. Postfix and prefix increments, these might be important for non-trivial iterators. They usually compile down to the same thing when it comes to integers. But when you say non-trivial iterators, maybe the compiler isn't allowed to elide that copy or optimize that away. There are equality and ordering requirements on our types. In fact, we'll come much more to this. There are, in general, requirements on the types that come into our algorithms that we need to carefully consider. Another operation that's important is halving and doubling, distinct from generalized multiplication or division. Because for a long time now, computers have been able to halve and double things very, very quickly compared to how they can multiply them in general or divide them in general. In fact, there's a famous story about this. The most famous algorithm of them all, the Euclid's greatest common divisor, it stood for 2,000 odd years. And then there was an Israeli researcher called Joseph Stein in 1967 who was working on hardware that he couldn't, necessity was the mother of invention here, and he had to come up with an alternative formulation to the classical GCD algorithm, and it's based on his algorithm is based on halving and doubling, and he came up with a formulation of greatest common divisor which was potentially more efficient than the classically known one, which has stood for 2,000 years. And it's this idea that halving and doubling should be considered a separate operation from generic multiplication. There's a question: would it be recommended to relax it even more with ADL with using idiom for customization points for next and so on? Not. If I understand the question, I'm going to say it's outside the scope of this talk. Maybe. I don't want to get too deep into library fundamentals and that kind of thing. This talk is more focused on, how to craft the algorithm. The customization point at the end of the day, you could choose a few different ways to do it, perhaps. Yes. The last operation here is something that we would have said if I was giving this talk 25 years ago. I would have said, generic multiplication and division, we should manually strength reduce those. But I think these days the compilers do a fantastic job at that, and generally we should try to write readable code and not go to the level of obfuscating those operations in the algorithm, because at some point the compiler can be relied on to do that stuff. So let's talk more about the requirements on types, because Eric Niebler did make this observation. It's a very true observation. Concepts are constraints on types, but you don't find them by looking at types. You find them by studying algorithms and seeing what the algorithm requires of the types. So here's our code as it stands after strength reduction. We've got our forward iterator coming in. We've got a stood distance, stood next. This is exactly what you saw, a dozen slides ago, however many. So this algorithm is coming along now. There is a lurking issue. No one's put in a question about it yet, so I will just tell you. If we compile this with W conversion, the issue is that the thing returned by stood distance here is a signed type. And we said at the top of the talk that we were using unsigned. And so on that line where we compute the stood distance and assign it to an unsigned quality, we get a compiler warning, basically. So we can get around that just by putting in a static cast. For now, it seems okay. Does it add any assumptions to our algorithm? Not really. Don't think so yet. We'll go with it for now. But, maybe there's another problem here that you're seeing, which you're practically shouting at the monitor to me. And I know several people have been shouting at the monitor, I'm sure. And that is that, where's the const? Where's the const expra? All right. So we put in const everywhere. We put in const expra everywhere. There you go, Jason. That's done. Fairly easy to do that. right? But and you think that's trivial, and maybe you'd start out there. But it's important to consider kind of every little thing that we do to change this code up, to sort of polish it up. Okay, pretty good. Now this value that we are passing in, and we're passing along in our sort of putative recursive calls to the algorithm, presumably most of the time it starts at 0. Like the common use case maybe for our algorithm here is going to be, you want to find a gap and you're just going to assume that everything starts at 0. So maybe we should add a default argument for easier call size, just to ease the interface a little bit. Default construction here of value construction is going to be kind of analog to 0 for whatever type we pass in, presumably. Now, you don't always want to provide default arguments, and in general, default arguments aren't really as good as function overloads. We'll come to talk about that in a little while, but I think at this point it's reasonable. So we have a reasonable algorithm. Let's think about the preconditions and postconditions here, and let's document them even if we don't have contracts yet. So the preconditions are that our range doesn't contain, there is actually a gap. Okay, or there is in some sense, the gap might be at the end, but there is a gap in T's. A precondition which is actually, I think, still like really difficult to, or maybe impossible to say in the contracts even, is that last is reachable from first. It shouldn't contain duplicate values. Maybe value should not overflow if it's signed. That might be a precondition. Perhaps, or just a condition on the function. Often we would choose to deal with conditions like that being UB as just that's a condition that the caller has to deal with, right? It's too onerous for us to deal with that sort of thing in an algorithm, perhaps. And the postcondition is that we've permuted the elements. We also, of course, have to think about a better name. Now, I'm in a position where I can't interact fully with you. But up till now, we've been going along, and I don't know if you've, well, I won't go back, but it's been find missing element. I just put that in there, and none of you said anything about it. Of course, I can't hear you say anything, but nobody said anything about it. But let's think about the name. It's a bit verbose. It's not completely descriptive because we find the smallest missing element when there isn't just one. We also, the find functions, Arthur O'Dwyer pointed this out to me, that the find functions in the standard library generally return iterators, and we're returning a value, not an iterator. So maybe it's preferential to say, rather than find X, return some kind of min, because min returns a value, although min element returns an iterator. So, reasonable people can differ, but I've had suggested find first vacancy, find a vacancy. I used to say min unused. I'm going with min absent for this cut of the talk. That's the one I like best at the moment. So that's the one that's going to be on the slides. So this is our final version, is it, at this point? We've talked a lot about how to mold the algorithm and how to make it generic without losing efficiency for the iterator categories and such. But now we come to the actual important topic of really figuring out the type requirements. And to do that, we need to test with more types. So I mentioned moving beyond integers. I commonly want to find a gap in things that I've scheduled. And to do that, I might need to find a chrono duration gap. I'd really like to work for this case. But what's the problem here? The compiler says it can't call next when I give it first and half. So something wrong with, I know first is an iterator and that's fine. Something is wrong with half. It's not the right type. Why is it not the right type? Because we've got a duration. M is going to be a duration. We know that value is a duration. Half is a signed type. Half is a distance type. So this is where we move beyond the ints. Considering just the ints kind of made us think a certain way, and here's where we move beyond that. What we need is to make that distance type into a chrono duration. So we need whatever we pass in the t at this point, it must be constructible from the integral type. So we'll take the static cast off that call to off that half declaration, and we'll move it onto the point where we're actually making the t again. And this is okay. Yeah, this works with chronodurations. Now we're passing the right thing to next, because half is now the distance type with next requires. We're doing the minimum conversions, but this kind of told us about a crucial requirement for our algorithm. There is in some sense a correspondence between integers, between the values we pass in and the integers. Doesn't mean to say that the values are integers, but there is a correspondence there. But, you know, there is some sense there's a mapping between the countable integers and our values. Well, once we tried it with durations, I'd also like to try it with time points. So, you know, I might want to pass in a vector of time points and find the missing time point here. And when I do this, it says now, oh no, I can't static cast along to a time point. I can cast it to a duration, I know that, but a time point is not constructible from just an integral type. So clearly we didn't quite think enough about that. There is a question, isn't ordering a precondition also? That the types are orderable? Yes, if that's what you mean to say. Of course, they can be in any order, but the fact is they must be orderable. Okay, so it works with durations. It doesn't yet work with time points. Why doesn't it work with time points? Well, this brings us to the notion of affine space types. And Bjorn Fowler and Adi Shavit have a great talk about this that you can look up at your leisure. The idea is that sometimes we have, for instance, in the case of chrono, a time point and a duration. And these types, although they're representationally the same, they represent a point and a difference. They're different types, and together they form this affine space. And there are a couple of examples in the standard. And it's fairly common, perhaps, that the point type is unsigned, while the distance type, the vector type, is signed. And so we need to think about the type of the difference is a separate type from the type of the value. We need to account for this subtraction. When you subtract two values, you don't always get the same type that the value is. You might get a difference type. And so here we're using diff t to represent that. And then similarly, when we add a value, when we add a point and a vector type, and in the affine space, we add a point and vector, we can do that to get a point, right? And that's what we're doing on that line where we static cast the half to diff t now, which is the difference type. So here's, in some sense, a more final version. This is pretty good at this point. Of course, you can go on, you can iterate, you can always add more. You can make this adaptive. Some point that I'm not going that far in this talk because I only have an hour, but there are important further things you can do here. But, in terms of making this generic, a lot of the things that we've had to think about go into any algorithm and making it generic. So what we need to do now is document our behavior. In particular, we should document the type requirements that we've discovered. We should document the return value, of course. We should document the complexity guarantees and how they vary by iterator category, how many swaps we're doing, how many copies, constructions, conversions, that kind of thing, how many comparisons. For all of the standard algorithms, you find this information on cppreference.com. And lastly, or at least lastly in this list, the exception behavior might be an important thing to document. So at this point, someone usually asks a question because they've seen this, and this strikes them as an old style algorithm. It's using iterator pairs. Why isn't it using ranges? Here's where we get to talking about that. So ranges are great, an important part of C++20. They don't give us many extra algorithms yet, and to me they don't fundamentally change the process of making algorithms. What they give us is laziness, great, and they actually give us a whole lot of, because they move a lot of algorithms into range views, they sort of give us algorithms in the iterators. So, and that's what people mean really when they say they're composable. They mean these algorithms in the iterators. They don't like, it's not any different for stable sort and algorithms which we still have to, we still have to actually move things around, and we're not able to put them in views. The real composability comes in the views. And we get all of these things embedded in range views. We get projection functions everywhere. It's like we get a unary transform everywhere. We get things like reverse, copy, find, remove, all your basic algorithms. And we get all the iterator runes, as Jonathan Baccara called them in his 105 algorithms talk, sort of baked into and composable in the iterators. So if you want a counted, reverse, move, sliding iterator, you can have one in at least eventually in standard ranges. So that's a smaller side about ranges. They're great, but they don't fundamentally change the concerns of writing an algorithm for me. Something else you might want to do with our algorithm is to provide overloads. We saw that we gave it a default argument. We might want to provide a range-based algorithm. We might want to change the predicate on our algorithm. For this algorithm, I think you could like run it either way around from min or max, but I don't think a generalized predicate would have to tie in with how we define where the things are, so with the orderability. So I'm not sure yet how to make that work in general terms for this algorithm. Now, when I first gave this talk, I gave it in this style, and then I realized that min absent, we've implemented it with partition, but we could also implement it with min element. So instead of partitioning a thing around a value and then finding out where that is, flip it on its head and say, let's pin where that is and find out the value. That's what nth element does rather than partition. And so I coded this up and I put it on Quickbench, and it was about 25-30% slower. But it was useful to look at, right? And here it is with nth element. It's basically the same. The useful line here is where we say inside that if, init is star mid plus static cast diff t of 1, right? That tells me something about t's or about diff t's. It sort of elucidates the requirement on the input. You have to be able to construct it from a 1, right? What I said about there being a correspondence between integers and values, that's called out right there in the code. So these different formulations can tell you things about the algorithms. There is a question. I think I can't answer it now because I need to push on, but I will answer your question at the end, Victor. Thank you. So now we are done with that case study. Now I want to talk as an epilogue about the generalities of building algorithms. Let's talk about arguments first. So there's an important question: what order should we use for the parameters? And this actually determines a lot of things about functions, including sometimes their names. So option 1 is do as the standard does, and you're never really going to get in trouble for this. So in general, where we have an execution policy, it would come first. Then we take our input iterator pair or iterator count. Then we do any other input iterators, then some output iterators, then any initialization value, for instance, with accumulate or with our algorithm here. Then some kind of predicate, and finally, maybe a projection or transformation function. And there are examples in the standard that have all of these. And if you look at the standard, most of the algorithms do follow this. The transform reduce style algorithms annoyingly take the reduction operation before the transform operation, but most algorithms in the standard follow this pattern. Another option is order the arguments according to the partial application you wish to see in the world. So this can mean putting arguments that that vary frequently at the end, so that you can bind front the first ones. Although to flip that on its head, it could mean putting arguments that change least at the end, because you can default them, maybe. There are choices. Sometimes you get the order imposed on you by the language, because if you're using defaults, either in the template types or in the template arguments or in the runtime parameters, you have to do certain things to default them. There aren't any variadic algorithms yet, but we can imagine what their function signatures might look like. So I said it informs naming. This is especially true with binary functions, I find, because I like to imagine binary functions as being infix. So if you put the arguments the first way around here, the right name for the function it starts with, because the string s starts with the prefix. But if you flip them around, and you might have good reasons for doing that, then the name of the function would become to me is prefix of, because if it were infix, we'd be saying prefix is prefix of s. So there are 4 algorithmic principles listed in the work of Alex Stepanov, and I'd just like to highlight them by way of epilogue. The first one is the law of useful return, and that is that when you're inside your algorithm, if you're computing something which is useful to the caller, return it, right? It might not be the thing that you are computing sort of as the name of your function, as your primary job, but if it's going to be useful, if it's going to be difficult for the caller, maybe the caller can't actually compute it themselves, or maybe it's going to be difficult for them to compute it or takes extra time, you should return it. All of the potentially useful information. A good example of this is rotate. In C++ 98, it returns void. In C++ 11, it returns the iterator where the first ended up. And this is so useful. This is a potentially useful thing, a very useful thing. It computed, it returns it now. And because of that, it's much more useful as a building block algorithm. Unfortunately, there are some areas where the standard is deficient. Copy n, and in general, n algorithms, they need extra special care with the law of useful return, because copy n returns an output iterator, but you're passing it an input iterator. So where does that input iterator end up? It doesn't return it. You have no way to recover it if it's truly an input iterator. This is kind of unfortunate. The good news is this is fixed with ranges, which returns both iterators. And this is, take care with iterator count versions of algorithms. So return all the potentially useful information you compute. Doesn't mean do extra work. It does mean pay attention to, in particular, the non-random access iterators, which are going to require linear time for the caller to recover where you got to, and just be on the lookout for free stuff. The second law is separating types, and this is where it can actually help to physically print the code and take a highlighter to it, and then discover which variables interact with other variables, and what operations they use. And we saw some of this when we did, when we looked at separating the types, separating the affine space type. Don't assume that one type is the same as another type when they're different variables. Try varying them and see where you go. And there's a famous sort of example of this, or sort of, so this lecture, part 5, parts 1 and 2, is sort of the extended version of Sean Parent's famous lecture from Going Native 2013, from whence we get no raw loops. He describes where, by looking at stable partition, he discovered that it only moves the element after testing it with the predicate, and therefore that means that the predicate information can be kept in an entirely separate data structure. You can store your selection information, I think it was in his case, separately from what's actually being selected, because this stuff gets moved around, and this selection information is just used in testing the predicate before it gets moved. So it's going to, give you that freedom. So don't assume two types are the same when they may be different. The third is the law of completeness. And this is the one where we get to say, well, let's provide the range operation, and let's provide the user predicate, and let's deal with all of the different stringish types that we have. And we've seen this sort of design space exploration often comes out of the separating types that we do. This is another case where the standard does fairly poorly. It doesn't have very many _n variants, but I've had use for things like accumulate n, which are fairly easy to code up, in this style. But the standard isn't there yet on many of this stuff. With ranges, we will get all of those iterators, perhaps, so it might get better. Here's another example from the standard. Set symmetric difference could really do with another output iterator, or even another 2. Because commonly what I would use set symmetric difference for would be, I've got a before set, I've got an after set. I want to know what got deleted, what got added, and what stayed the same. And so, the only algorithm that has more than one output iterator in the standard right now is partition copy. But set symmetric difference could well do with a couple more variations. Transform exclusive scan is another example where, for some reason, transform exclusive scan or inclusive scan, they don't have the binary range versions. They only have the unary range versions, despite the fact that transform and transform reduce both have the binary versions. So try to provide all the complete things. The final law, and the most difficult one really, is the law of interface refinement, which is to say, we don't really know what the right formulation of interface is until we've had experience, sometimes extensive experience, meaning maybe a decade of use. Literally, something take years to refine. And the famous example of this in the standard is max, right? So when the 2 elements are equal, min returns the first element, and so does max. And that's an arbitrary choice that Alex Stepanov had to make back in the day. And with hindsight, with a decade and more of hindsight, it's become clear that this wasn't the best choice, because it doesn't become clear until we start using min and max actually to build up algorithms like stable sort and to think about things like stability of comparisons. The better choice for max would have been to return the second one in the case when they're equal. And this kind of thing doesn't come up, from the get-go. You actually need experience, and this is a really hard thing. Rotate is another example of that, right? We saw it in the useful return. It's another example of refinement coming years later. So the 4 algorithmic principles: useful return, separate your types, offer completeness to the callers, and do what you can to refine the interface. Again, it requires time, but you're not done after you release the first version, I think is what we can say about that. So we started out, why would we do this again? We started out with necessity. The standard set of algorithms isn't complete. It was never designed to be complete. It was designed to be a model for building our own algorithms in a generic way. And we have this advice, no raw loops. So what we learned along the way is that actually examining the algorithms and building them gives us insights into the nature of the problem. It allows us to generalize, maybe to specialize. And this is what algorithmic intuition is. It's seeing how one problem is like another. And to do that, a great thing to do is to try and build the algorithms to solve the problem and see how they can vary. It shows us the constraints on our data, how it really interacts. It can allow us to reformulate things, and it can allow us to identify efficiencies. In the end, all of programming is applying algorithms to data structures until you get a data structure you can print out or display to a human in some way. Algorithms plus data structures equals programs, as Niklas Wirth, I think, once said. So again, what to expect from ranges is that it's going to expand that completeness section. It's going to expand the variations that we can easily use. But that's not a reason not to continue writing variations and continue exploring new algorithms. So I'd like to wish you happy coding. I'd like to tell you to study the algorithms and write your own and have fun with it. Thank you very much. And I will answer a few questions. So the question, why is it bad that max returns the first argument? So this has to do with what happens when you use min and max to build higher order algorithms and you consider stability of sorting. I think it's stability in particular. Min, if you're comparing X and Y, min should return in some sense mostly the thing on the left if they're equal, and max should return the thing on the right when they're equal in order to be stable. And it's that kind of thing that is really not obvious when you first write min and max. Like I say, you just make an arbitrary choice. It only becomes apparent years later that there was a better choice. I will absolutely make the slides available to the person asking that. Yes. Someone asked, is it justifiable to use a raw loop instead of an algorithm if the raw loop is clearer? Okay. The definition of a raw loop is a loop that does more than just its job. So by definition, a raw loop is never clearer because it does more than one thing. In addition, raw loops tend to accumulate cruft over time. They don't have names, and they are frequently, there is frequently not an efficiency argument to be made for raw loops either. So I would nearly always prefer a well-named function that is going to do one job. One more leftover question. Can I talk about the requirements on T? Regular, is it regular? Are there operations required on T? Do they need to form a monoid? I think in this case, there is no monoidal requirement from the min absent algorithm, I think. There certainly are monoids to be found in there, I expect. And some of the requirements we talked about, T needs to be constructible from an integral type. There are probably there are no swaps in there, but yes, we could look at that algorithm and see how T is constructed, how it's copied. Movability is usually required. Yeah, regular is good. Sometimes semi-regular, which is to say regular up to, but not including the ordering constraint. So equality is needed, but ordering is not. That's fairly common. These are all things to think about as type requirements when you build algorithms. And I think with that, I'm not seeing any more questions. So happy coding, and thank you for coming to the talk.